For this example, notice this example takes over a page of the handout, and so hopefully you've read through it before you got to this video. If you've not read the example yet, please read the example before watching this video, because what I'm going to do is I'm going to do it in a different order in the video than on the handout, and that's on purpose because it's good for you to read it on the handout the way it is and test yourself to see how you're understanding these things in this class so that you know how much you're learning by the time we're wrapping up this chapter. And then watch the video. After you've done it yourself, watch the video and see if you can't learn even more by seeing things mixed up again or just done in a different order. So I'm going to go to that matrix for this problem. The example says, consider the space spanned by, this is on the top of the previous page. On page 5 it says, consider the space spanned by, and it lists 5 vectors. And so that can be captured as a 3 by 5 matrix. And so the first thing I'm going to do is, just like on the handout, in order to reduce the column space, those 5 columns, it turns out only 2 of them are independent. We don't even have 3 independent columns, only 2 columns will be independent. And so to reduce that, to find a basis for the column space, to reduce dependencies, we use the row reduction operation, or the process, Gaussian elimination. And so I'm going to show on the whiteboard here the transpose of that matrix. So it's the 3 by 5 matrix, but switching the rows and the columns. And so you'll see column 1 is entered into the first row. Column 4 is entered into the 4th row. So if we enter the columns as rows, then we can do RREF. And that's where we get that result that's on page 5, the previous page, way up there. And so reducing these rows gives us these 2. These are the only 2 that we need of independent rows. And so these, transformed back to columns, become the column space. I have an arrow pointing up to them. The 2 of them are in the independent vectors that would span the column space. But look what else we got on page 5. We also were able to represent the column space as solutions to a constraint equation. If we switched that back and remembered that the third one is the free variable, or the free row, we put a 1 there, moving the rest of these two numbers over would make them negative, and so the column space would be described by this one single equation. There are 3 unknowns, or those column vectors are in R3, but it's a 2D space, and so one constraint equation. Notice that I wrote this on the whiteboard on purpose, different from the way it is on the handout. Is that okay? That we can have an equation negative 1/5 x1 minus 12/5 x2 plus x3 equals 0, and call that the same thing that's on page 5 of your handout? Just multiply both sides by -1 and see if you get the same thing. So what I'm going to do next, this is what we call the left null space. It's the same process we used for finding the basis of the null space, but there's some transpose things going on. But if we row reduce the columns, we not only get the column space, but do you see how by reducing the columns we got the basis for the left null space for free? So I'm going to switch the whiteboard. So here the whiteboard is changed, and now it's row reducing the actual rows of that matrix. When we did this before when we were solving systems of equations. When we solve systems of equations, we row reduce, and we automatically get a basis for the row space. But then remember, we also used this to get a basis for the null space. If we're solving equations that are equal to 0, then this would be a row of all zeros. And that's okay, they're still solutions, but they're infinite solutions. And so we learned about identifying these, what we called free variables. They're free because the solutions could be any combination of these three basis vectors. And so we would move these over. This, what I have in a squares here, would be moved over. So there'd be a positive 2, positive 1, negative 3, and a 0, negative 2, positive 2. And the free variables are identified as the second variable, and then the fourth and fifth variables. And so there's this identity matrix thing that always goes on inside here, and the rest of these numbers come from the result of finding the basis for the row space. So the row space and the null space come from the same row reduction, just like on the previous whiteboard. The column space comes from reducing the columns, but that also gives you the left null space.